Check your answer. Should have had syn addition of H and OH. Well, where's that H? It's not drawn. In a lot of solution manuals, they're not drawn, right? But I do recommend drawing it to work it out. So I'm just going to show you how I would solve this real fast in case it didn't match. But I'd say I know it's syn H, new H, right? And OH. And it's also, so that's the stereochemistry. Regiochemistry is anti-Markovnikov. That means OH goes on less substituted carbon. So I'm going to find the less substituted carbon. It's this one, the one that doesn't have that R group. That's going to get the OH. Pick a dash or wedge, whatever you want. So, because you're going to have to draw the other one too. So I'd start with a dash. That takes care of my anti-Markovnikov. Now to make it syn, I have to make the new H a dash, which forced the R group that was pre-existing to be a wedge. Of course, I must be able to make the enantiomer, which I could draw as the mirror image or just do the exact opposite. Because I could have both dashes, I could have both wedges. You can't have one of each because that would not be syn, that would be anti. That forces the R group to be a dash when these are wedges. So you do indeed form a racemic mixture, which might be represented that way or just written as racemic. These are one and the same. So the H's are not always explicitly drawn in, but if you do draw them in, it'll help you visualize what's going on there. Syn H and OH, right? Anti-Markovnikov, meaning the OH went on the less substituted C. Okay, hope that helps recap that for you, because we're going to move on to another hydration. It's our last one. We're doing 3. This one is called oxymercuration demercuration. I'm going to draw the product for you. See if it looks any different than if you could have formed this product another way. If you thought, well, I know how to do that with acidic water, you'd be correct. So this is the so-called acid-free hydration. Almost like it's a commercial. It's acid-free because acids can pose a problem. If you have a large molecule with lots of functional groups, acids might react or interfere with them. So it's good just to have something, some other pH-friendly reaction ready to go if it's not friendly for an acidic environment. So acid-free, so oftentimes if we learn how to do something in acidic conditions, we might learn basic conditions as well to accomplish the same transformation. And this is essentially like basic conditions. It's sodium borohydride, which is a H-. The function of sodium borohydride is to add the final H, that new H. So it's our H source, our hydrogen source. So remember we have, if you look at the net change of what happened here, let's draw on our H's that are missing. This is that same carbon right here. It still has those 2 H's, but it's going to have a new one. Where did that new one come from? I'll just choose that to be the new one. That came from this step. Okay. So also over the arrow not shown, which needs to be drawn in, is either this is with water or alcohol. So if you had alcohol, it would be OR there, but if you had water, it's OH. So it's hydration if it's water, otherwise you can make an ether. So why do we have the NaBH4? NaBH4 is something you want to get used to. It's sodium borohydride. It's a source of H's. It's a reducing agent. What it really does in this mechanism is it replaces the HGOAC from step 1 with an H. So step 1 gets that kind of that regio chemistry worked out, which by the way is OH on the more substituted, H on the less substituted, so Markovnikov. And because of the nature of the mechanism, it is not stereoselective, just like the acid-free one. Unlike the acid-free one, there are no rearrangements. No rearrangements possible. That's the benefit. Because we don't form our usual carbocation that can just rearrange. We form sort of, it's an unusual mechanism, so we'll have to explore that in a little more detail. So let's spend some time on that. So yeah, that's why I have the Markovnikov there. So remember, it is another way to get a Markovnikov alcohol, but it's not always going to give you the same product as the acid version, because if a rearrangement was possible and you did not want it to happen, this is a good route to go. If you did want it to happen, then you want to stick with the acid version, right? Okay, mechanism. First, we're going to look at what's over the arrow. Look at that first step, mercury acetate, HGOAC2. We're not really used to using that, so let's write that up. First of all, what's acetate? OAC minus is a common anion, acetate. That's the conjugate base of acetic acid, resonance stabilized, comes up a lot, often see it as a leaving group as well. And that's what we'll kind of view it as here. So if you have these two together, it's also in equilibrium with the dissociated form. So we'll use this guy right now to react with our alkene. So let's take our alkene. I'm going to lay it down on its side just so I can really focus on that pi bond. And I'm going to bring in the mercury that's positively charged. It just looks more reactive that way, right? So you can choose to do it after you let it dissociate, or choose to attack it here and let it kick off. So some books do it in different orders, but it's the same sequence of steps. So we say, oh, that looks electron poor. An alkene would like to attack that, right? Now we have to ask a question. Every time we add to a pi bond, two carbons are affected. One gets the bond, the other one gets the charge, positive charge. So we say, who would be a better positive charge? Better beholder of the positive charge, A or B? Definitely carbon A, right? That'd be tertiary. So we're going to let that one get the positive charge, let the electrons stay with carbon B, and that will be bound to the mercury, that new group. Now this, you say, oh, wait a minute, carbocations can do rearrangements, but hold on, this isn't your traditional carbocation. It actually engages in this unusual, for this book anyway, feature called sigma bond resonance. We don't allow sigma bonds to participate in resonance normally, but this is something that is a special case. Sigma bond resonance. So that means, yes, I'm going to write a resonance arrow. I'm going to put the mercuric acetate to make a 3-membered ring intermediate that's strained, just like a bromonium ion, right? So the only difference between these two structures is who has the charge and whether that bond is there or not. So we're moving electrons around. We didn't change anything else. We didn't actually break this bond off, right? We just added another bond to this one, right? So this is a special, it's not considered a step, it's considered a resonance structure because it's still attached here. So this one is one of the two. This one's actually the more commonly depicted because this doesn't behave like a carbocation, even though this is strained. So we believe this to be a very weak sort of bond here, weaker than this one. So in other words, it's a hybrid between these two. And like all resonance structures, we can draw a hybrid. So let's draw the hybrid. So that would mean, remember, a resonance hybrid is the average of the two. So we take everything that's always there, those get solid lines. The charges are not always there, so those get deltas. And then this is the one bond that's not always in both of them. So that gets a dotted line. So we're going to draw that 3-membered ring, which, by the way, before I go any further, it has a name also. mercurium ion. It's an intermediate. So the hybrid will look something like this. Dotted line, Hg, delta plus, OAC, there. So the key here is to see that we have carbocation character there, but it's not a carbocation that could just go rearrange. It's kind of locked in this ring. So that's why we do not observe rearrangements taking this path. Yet we observe Markovnikov addition simply because we still favor the more stable carbocation to be formed, even if it is more in a hybrid scenario. Okay, so to continue the mechanism, we will bring in our nucleophile, water or alcohol, if you use that. I'm going to show it with water since we're really comparing the hydration at this point. Attack that positive charge, and if you did draw the 3-membered ring, then you let that bond open. Aha, look at this. You may not have ever been happier to see an oxonium ion because this is the light at the end of the tunnel. This is starting to finally resemble, I mean, this looks nothing like our product, right? This is finally starting to resemble our product. We get an alcohol right here, and we're one deprotonation step away from that. But we still got to clean that guy up. So I think you would agree that we've covered some more complicated mechanisms lately, which means we are ready to take some more sophisticated steps in simplifying the so-called easy parts, the parts that should hopefully be foundational by now, which is proton transfer. So occasionally when you are knee-deep in a more complicated mechanism, you are going to see the following. We know that we can't do anything else in this mechanism until this is neutralized, which means we basically need to make sure we do this step. We lose the proton before we move on and do something else, because we're not going to create doubly charged intermediates if possible. So before we do anything else, we got to take care of that. Now, normally we define the appropriate base, show the arrow for the base, and then draw the arrow there, right? And you could still do that. It is never wrong to write too many steps. However, when you start to look in solutions manuals at this phase in the game, or answer keys, you might start to see, because the meat of it is complex enough, your eyes need to be directed to the curved arrows of the steps we're unfamiliar with. They will sometimes omit the curved arrows for deprotonation, just so your eyes aren't focused on something you already know, and indicate that we're taking that shortcut by saying minus H plus, and that we understand what that means. That means we deprotonated it to neutralize it. We still write out that structure, and you say, how hard is it to write 2 more arrows? It's not really that issue. They build up over time, and when the longer the mechanisms get, the nicer it is to have a little shortcut over something that's a little more, becomes tedious if you know it very well, right? But if you still feel uncomfortable doing that, you can write out the steps. That's not wrong to do. Okay, so minus H plus just means we neutralize, okay? Never be allowed in exam 1 or 2, but now we're getting to the point where we need to kind of see the meat of the argument rather than all the little other details that we already know. Okay, so that actually gets us to the end of step 1. That's our step 1 product. Remember step 2 had sodium borohydride? And its job was to replace the HgOAC with an H. So remember there's 2 H's here. There's still 2 H's there. Those are the original H's in the alkene. New H from sodium borohydride. Okay. We're not going to cover that mechanism or take the time to do that. It's complex enough, and the regio and stereo selectivity was already proven with the first step, which is usually our main goal with looking at mechanisms, understanding why we got regio and stereo selectivity. So if I were to clean this up and not draw every little H that's on a carbon, it might look more like this in your answer key, right? And we're done. All right. So know how to do the first step because that helps you get to the bottom of why the regiochemistry is the way it is, why it doesn't rearrange, why we have the loss of stereochemistry, because we have a carbocation, but we don't. We have a carbocation, hence we lose stereochemistry, right? We have a carbocation, hence we have Markovnikov selectivity. But we kind of don't because we never see rearrangements, even if they look like they'd be possible otherwise. So rearrangements don't happen. So that means we have a hybrid and kind of in between the two, which is represented by that hybrid there. Let's put this all together. I want you to try this one. In order to try it, I'm going to give you a little head start. D is going to come up a lot in the future. What is D? D is sometimes called heavy hydrogen. It's the hydrogen isotope that's 2 AMU. So deuterium. It has its own symbol, D, and it's used for labeling purposes, tracking. So sometimes we're not writing out the mechanism every single time, but we're tracking it with the D. So when you're asked to predict the product, you might need a little mini mechanism to help you, but the objective of this kind of question is to write the missing product. So your own scratch work showing the mechanism is a good idea, but when you finally get here, knowing that the D is in the right spot sometimes proves that you knew the mechanism. So that's very common on homework problems, exam problems, but it's also useful in the lab for labeling and tracking and getting to the bottom of what a mechanism might be. So I want you to get comfortable seeing those. So we're going to start putting those in our examples. Oftentimes the deuterium is just replaced what normally would have been a hydrogen in a starting material, or what normally would have been a hydrogen or proton or hydride in a reactant over the arrow. It reacts like hydrogen in these kinds of reactions, okay? Reacts like H. So treat it like an H, except for you actually have to write out a D instead. So you're not allowed to imply it. Okay? So oxymercuration, demercuration, syn, anti-Markovnikov addition of H and OH, and the very first one, acidic water. All of these add water in some way, and the alkene's gone. You draw the products. Okay, and check back with me.